Greetings everyone, I am M. Katyayani from 3rd BSc Mathematics Aider. In this video, we are going to see about the differential equations and the fundamental concept in differential equations, simple electric circuit. Differential equations are the fundamental concept of mathematics and physics, helping us to describe real-world problems using equations that involve derivatives. We explore one of the most important applications of differential equations, electric circuit. Before diving into differential equations, let's recall some key electric concepts. See the circuit, it involves resistor, inductance L, and the circuit also contains a capacitor. This circuit consists of 4 elements. E is the source of electromotive force. Electromotive force is the energy per unit of electric charge that a power source like a battery or generator that provides to a circuit. It follows E may be a constant or a function of time depending on the nature of the resource. R is a resistor of resistance or opposing the current and affects a drop in EMF of magnitude. It follows the equations ER equal to RI. This equation is a Ohm's law equation. We know that Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. V equal to IR. L is an inductor of inductance L. It opposing any change in the current by producing a drop in EMF of magnitude. It follows the equations EL equal to L into di by dt. Next C. C is the condenser of capacitance C. It was designed to store the charge Q. The capacitor gathers charge and this resists the inflow of additional charge and the drop in EMF. Arising from the factor is it gives the equation EC equal to 1 by C into Q. Since the current is the rate of flow of charge and hence the rate at which the charge builds up on the capacitor, we have always I equal to dq divided by dt. Now, by Kirchhoff's law, this algebraic sum of the electromotive forces around a closed circuit is 0. Kirchhoff's law gives when there is no capacitor. That is, Kirchhoff's voltage law states that the sum of EMF and potential difference in any closed loop of an electric circuit is always equal to 0. That is, input and output is addition is 0. Kirchhoff's voltage law in the presence of multiple EMFs and voltage drops. Therefore, we get E minus ER minus EL minus EC, that is RLC circuit. E minus, substituting for ER, EL and EC, we get E minus IR minus L into di by dt minus Q by C equal to 0. Left E on the right hand side, E equal to IR plus L into di by dt plus Q by C. We may regard either I or Q as a dependent variable. Let's take I as a dependent variable and also we eliminate Q by differentiating 1 with respect to T. Next, we substituting I for dQ by dt. Hence, d by dt of E, which is equal to d by dt of IR plus L into di by dt plus Q by C. Now, differentiating only IR, R is the constant. So, we get d by dt of IR equal to R into di by dt. Then d by dt of L into di by dt is L into d square I by dt square. Substituting this, we get R into di by dt plus L into d square I by dt square plus I by C. Since Q is dq by dt equal to I. When we differentiating Q, we get dq by dt and substitute dq by dt for I. To eliminate I, replace by I by dq by dt. It was reduces to IR equal to R into dq by dt. Equation number 1 is reduces to IR into dq by dt. Next, L into d square Q by d square Q divided by dt square plus R into dq divided by dt plus Q by C equal to E. But primarily we are interested in the case when no capacitor is present. Hence, equation number 1 is reduces to L into di by dt plus Ri equal to E. Consider equation number 4 with simple initial conditions. That is, initially the current is I0 and also the time is 0. The constant EMF E0 is impressed on the circuit L into di by dt plus Ri equal to E0. Separating these variables, di divided by E0 minus Ri equal to dt divided by L. Integrating this, log of E naught minus Ri into 1 minus 1 by R equal to T divided by L plus C. Taking minus R on the right hand side, we get log of E naught minus Ri equal to minus R by L into T plus C. Now substituting for T equal to 0, I equal to I naught, we get log of E naught minus R into I naught equal to C. We get a constant value C. Next, E naught minus Ri equal to E naught minus R into I naught into e power minus RT divided by L. Now solving for I, we get I equal to E naught divided by R plus I naught minus E naught divided by R into e power minus RT divided by L. This shows that I consists of two parts, that is steady part and the transient part. The steady part is E naught divided by R and the transient part is E naught minus I naught minus E naught divided by R into e power minus RT divided by L. Now this tends to 0 as T tends to 0. Then we get E naught equal to R into I naught, that is Ohm's law is nearly true. Note that if I naught equal to 0, then this transient part I equal to E naught divided by R into 1 minus e power minus RT divided by L, and if E naught equal to 0, then I equal to E naught into e power minus RT divided by L. We get this solution. So in this video we explored how differential equations are used in electric circuits, the role of Ohm's law and Kirchhoff's law, how RLC circuit behave our own time using first order differential equations. Differential equation helps us to model many real world scenarios beyond the circuits, includes population generation, may transfer mechanical vibration. Now we see applications of differential equations. Differential equations are seen in electronic filters. In electronic filters, it is used in audio systems and signal processing to remove unwanted frequencies. Radio and TV tuning circuits. In RLC circuits, it helps in selecting specific frequencies for broadcastings. Heart pacemakers. Electrical circuits modeled with differential equations which regulates heartbeats. Power grids used in transformers and electrical networks to analyze power fluctuations. Mobile communications. It was used in wireless charging and signal transmissions rely on circuits governed by these equations. Thank you.